Returning to permutation specifically, but a very special case where instead of arranging the objects in a line, we're going to arrange them in a circle. So the question is, what's the difference? And it's all to do with the first object. Let me explain. If I put them in a line, remember our group of n people over there? And we're going to place them in a line. The line, if you think of them all as positions, I can definitely say that's the start of the line and that's the finish of the line. I can name each position, not a problem. So when I get that first person for this situation, then there's 6 spots I could put that first person in. Because if I numbered those positions 1, 2, 3, 4, 5, 6, I've got 6 choices. Now, a circle is different. There's the 6 positions, but which one is the start of the circle and which one's the end of the circle? Because it doesn't matter which one you choose. Say I decided I want the top one to be, and you chose the next one. Yeah, that's fine. Whoop, I'll just turn the circle. So every position could theoretically be the top of the circle. So when it comes to arranging the first object, there's only one way I can do it. And that is, I'm going to put it in the circle. Because it doesn't matter where you put it, I can rotate it to wherever I want it to be. Now, once that first object goes in, the positions are now defined. Because once you have an object there, I can say, oh, well, say you did pick the top one. I can say, oh, well, this is the first one next to that position. This is the second one. And they won't change now because it's all in reference to the person that's gone into the circle. So that's the difference between the two. So in the line, we start off with n objects. We say, right, there's n positions for you to go in. With the circle, I'd say, well, there's only one. You're going in the circle. Now I'm going to get the next object. Well, both of them now are n minus 1. Because now the circle is defined. I said, well, there's n minus 1 spots I could put you in. I could put you next to that person, or I could put you 2 seats away from that person, or 3 seats, and so on and so on. And the third would be the same, the fourth would be the same, all the way down to the last object where there'll simply be 1 spot left. So what does that mean? Well, it means that the number of arrangements in a circle are basically n factorial, same as in a line, but I'm going to divide it by the number of ways I could have put the first object. A bit like turning a permutation into a combination. So, well, I don't care where you put it, it's going in a circle. So there aren't n. Divide that, effectively I've got n minus 1 factorial. So all we've got to do is simply subtract 1, and we've got the number of arrangements. So, okay, a meeting room, and often in meetings you sit around in a circle. We've got 10 chairs. So we're going to have a committee of 10 people, and yes, we're going to allow 3 teenagers to be on this committee. How generous of us. How many arrangements are there in which all 3 sit together? How many ways can I do this? Well, the number of ways the 3 teenagers, because remember, they're going to still the same idea. The 3 teenagers are going to be in their own group. So we sort that out first. 3 factorial ways. I haven't put them in the circle yet, so it's still 3 factorial, just like a line. So 3 factorial ways for the teenagers. But now I'm going to multiply it by 7 factorial. Because I have 3 teenagers, 7 others, so that's 8 objects all up. But I'm going to place these 8 objects in a circle, not a line. So instead of 8 factorial, it's 7 factorial. And it turns out to be 30,240. Well, we're going to hold an election for chairperson and the secretary. What's the probability that they're seated directly opposite each other? Forget about the teenagers sitting next to each other now. So no restrictions, 10 people, going to put them in a circle, 9 factorial, so 1 less. That'll be the bottom of my fraction for this probability question. Now, with restrictions. Well, president, for some reason we've changed the chairperson is now a president. But anyway, they can sit anywhere. So they're going to be the first one in the circle. We're going to say, well, go for your life, El Presidente. Go and sit down. 1 spot. They're just simply in the circle. Times 1, because the secretary, you got to sit opposite. So there's now only 1 seat the secretary can go in. The other 8 people are now going to go in the circle. But because the positions are now defined, it is going to be 8 factorial. It's only when you initially place in a circle, you subtract 1. Once someone's in the circle, positions are defined, so it's exactly the same as a line. So that's 8 factorial. So we get 1 times 1 times 8 factorial over 9 factorial, 1 in 9 chance. Of course, simple logic sometimes works out better. Think about it. Chance for the secretary being opposite the president. Well, there's only going to be one seat opposite from the president out of the 9 other seats. So there's a 1 in 9 chance that they sit across. So sometimes these questions, you can work them out a lot quicker with just logic. Let's have a look at an HSC one. 7 people sitting around the table. Part 1, how many arrangements possible? Okay, 7 people. There's no one in the circle at this stage, so we subtract 1, going to be 6 factorial ways of doing it. 720. 2 people, Kevin and Jill, refuse to sit next to each other. How many arrangements are now possible? Well, this is one of these ones where it's actually going to be easier to work out how many ways that they are sitting next to each other, and then subtract them from the total number of possibilities. So let's put them together. They're going to work out how many ways they could sit. 2 people in their group, so 2 factorial. Now we're going to place Kevin and Jill, now like we're 1 person, 5 other people, 6 objects, going to put them in the circle. No one's in the circle yet, so it's 5 factorial, not 6 factorial. We subtract 1. So 2 factorial, 5 factorial, 240 ways. 240 ways. Take it away from the total number of arrangements, and we get 480 ways that they're not sitting next to each other. Here's a little flow diagram, now that we've seen all the different situations. So how do we approach these problems? The first key thing is it a permutation or is it a combination? Now notice what we've got in this flow diagram. Permutations and combinations are all without replacement. As soon as the question is with replacement, you've only got one option, and that's to use the basic counting idea. So permutations and combinations is when it's without replacement. So then you ask yourself, well, have we got a restriction or not? Now, if it's without any restrictions, then we know, okay, let's make a decision. Is it a permutation or is it a combination? Is order important or is it not important? Now, if it is important, now we have to think about, am I putting them in a line or am I putting them in a circle? If it is in a line, then we're going to say, well, we're going to use all of the items. Maybe we only use some of the items. And then finally, if all the items are used, hey, are all the items different or are some of them the same? That pretty much covers all the cases that we look at. I mean, there are other cases, but that's pretty much the ones that we've looked at there. There we go. So 14G to finish off some questions on circles.